All right, so 5 more problems to finish this out. So in the first print here, I forgot to put lambda in the sentence there. So if you had the printout, there would be a blank spot. I'll correct that later. And then also down in the other part, I forgot to put the DE, the differential little chunk of electric field in there. So here's this problem. Uh, Long rod, thin rod, some length, and some point along that axis out to the right, call it point P, is A away from that. And so how do we uh, go at this business? So first, just to start with a general thing about the electric field, it is essentially uh, it's K times one of the charges over the distance squared. It is Coulomb's law, which is K Q1, Q2 over D squared. It's that force per unit one of the charges. So you don't have a product of charges, but you still have a product of the distance, or a square of the distance beneath it. So that is the formal classical definition of the electric field, Coulomb's constant, charge per distance squared. So if I want to pay attention to a chunk of this, and so chunk is a high-tech word for a differential piece. If we're going to use calculus, we need to do that. And so this, if I want to know what the little infinitesimally sized piece of this electric field is, well, the constant stays constant. That's kind of nice. And we're told up here that dq, little chunk of charge, is equal to lambda dx. So lambda is charge density. All right. So that means there's some little chunk of charge that I'm exaggerating its size. So you're calculus students, you remember the squeeze theorem, or you better, it's squeezing down to some tiny little infinitesimal piece. But now we're putting it in terms of a variable that is differentiable. Okay? I can't differentiate charge, but I can do derivatives on length, things that have that sort of Cartesian vibe, if you will. Okay? So knowing that, so now instead of having Q in there, I'm going to change it to lambda dx. And instead of, now distance squared, well, D is nowhere in I have L and A, okay? So uh, we have to uh, sort of think of this distance, as x, all right? We'll just call that x. And so if I'm going to do it at this point P out here, I have a distance of x plus a. That's what's squared. Okay, so this is my distance, is x plus a. So every problem of this type, you have to decode it geometrically. Otherwise, it's going to be very difficult to use calculus. That's why the book titles, analytic geometry, because you have to pitch whatever you're doing calculus on geometrically in that regard. So now I've transformed the classical definition of the electric field, kq per distance squared, into a differential form, and I changed q to something that's differentiable. Okay, so my guess is that when you were in calculus, this wasn't emphasized because in that venue, we're concerned about you getting the methods. Okay. And so we don't necessarily, when it comes time to apply it to physical systems, we're banking on that you have the method down. So now you can extend your concept to go, oh, that's why we need to do it that way. So ponder that. For now, just press the I believe button and we have it. So if we want to integrate, it tells us what to do here. Find the net field by integrating this differential of the electric field, this little tiny chunk of the field, over the length of the rod. Okay, so we could, that means that E would be the, well, let's do this first. Let's just sort of consider the integral of dx per x plus a squared. It's just kind of pull the calculus away for a second and just, how do we go about doing a problem like this? Well, we'd probably want to do a u substitution. So if you let u equal x plus a, okay, then you're going to get du, excuse me, per u squared, which means the integral of u to the negative 2 du, which means you get a negative u to the minus 1 plus some constant. Okay, which means that's going to come out as a minus 1 over x plus a plus the constant. So that's just the, what's the math angle on this physics problem? That's relatively, that's Calc 2, right? Or maybe Calc 1. Where did you first do u substitution? You do them in 1? I thought so, yeah. So that should be well within your reach. I imagine it's probably even in a table somewhere, but doesn't need to be since it's a u substitution. So we know what's going to come out of the box. The result of my integral is going to be the constants yanked away, so k lambda, and then evaluated at that, this minus 1 over x plus a. So my electric field, I can just go straight at it here. I'm going to have a minus k lambda. I'll just pull that minus out of the integral. And we're just going to 1 over x plus a, and we're going to evaluate it from 0 to L over the length of the rod. So you go through all of these motions, and you're going to have a minus k lambda times 1 over L plus a minus 1 over a. They get switched because of that negative sign in there. That's it. This is just a formula generating problem. It's not a... Now, if we knew the length and knew the charge density, then we could obviously do something about it. But that's not the goal of this problem. All right. So any questions on that? All right. Next problem. So in this one, so we have this semicircular wire, constant radius of curvature, otherwise it wouldn't be semicircular. Has a charge density of lambda. So we had a straight wire, now we curved it. So it's going to change our functions a little bit. Still going to be elementary trigonometric functions, doing integrals and stuff, so it's not going to be anything crazy hard. But we need to understand what we're dealing with first. So if I consider this right here, this would be some sort of piece of the electric field. There would be some sort of dE aimed at that chunk of charge right there. Okay, so right here we have a ds. That's a little chunk of arc length. All right, and that ds would be equal to r d theta. That's just the arc length formula in differential form. S equals r theta. And I can just go straight to the differential form. The only things that do change are S and theta, so they're differentiable. R is a constant. Okay, so now I've matched, if I'm dealing with a differential of the field, I need a differential of the arc length, which means I can integrate that, but it's going to be according to some angle. Thing to realize, though, is I do need this to stay in kind of Cartesian terms. So that means that this right here, this is going to be the y portion of that differential. And there's some angle associated with that. As always, you've got to put it at XYZ land, or in this case, XY land, since it's two-dimensional. Okay, so the X component is going to cancel out due to symmetry. Okay, they either pushing away or pulling in, but they're going to be equal and opposite with respect to the X direction. So we don't even bother with the differential according to X because it's just going to be 0 by symmetry. Okay, but it's not going to be 0 by symmetry on the Y because I have a semicircle. Okay, they don't cancel each other. There's not a circle above it to cancel it out. Okay, so just knowing that, and I guess we could state that, that dE in the X direction cancels. Sum equals 0 by symmetry. All right, so we have geometricized, if that's a word, the physical situation so that we have some expectation of how to set it up mathematically, and in order to do it by means of calculus. Okay, and you'll learn even more and like numerical methods for differentiation. Basically, it's fancy arithmetic when you get higher up in your engineering food chain, but it's another day. All right, so let's take a swing at how to do this problem. So let's remember electric field is going to, well, let's do this. The differential in the y direction, okay, is going to be the differential of the electric field, and it's going to be by cosine theta. All right? Why is that? Because the y direction is adjacent to the angle. Hence, cosine is the trig function that we use. Okay? Since there's an angle involved, we have to go polar on it or trigonometric on it. We have to do that. Okay? To relate that back to our x and y pieces of the puzzle. So now I've expanded what dE in the y direction must be, okay? And so then there's this piece of the puzzle. You have if it's an electric field, the K constant is involved, and it would normally be charge over distance squared, okay? I'll write it. I'll put R squared since we're dealing that. Actually, this would need to be dq, I guess. But really, we can't do that. It's going to have to be k and the lambda ds, okay, just like in the last problem, okay, but it was lambda dx because it was a straight wire. But now it's going to be lambda ds per r squared, and then the cosine theta. So we go, you can always count on your chunk of charge, your differential of the total charge is always going to be a charge density, be it linear, area, whatever it is, in this case linear, times the differential of that length. Since it's an arc length, and in this case, S actually does specifically refer to arc length, it's ds. But we've defined ds to be r d theta in our geometric setup. Okay? Everybody still with me? Nobody's, all right. All right, so we have our thing set up at last here, so we could write dEy equals k lambda, and instead of ds, I could write r d theta per r squared cosine theta, which of course can be written as k lambda. The d theta is going to drop out. I'm sorry, the d theta is not going to drop out. One of my r's is going to drop out, and I'll just have cosine theta d theta, right? So or in this case, cosine theta per r d theta, and then I can pull that r out, so I have k lambda per r cosine theta d theta. So really what I'm dealing with is an integral of cosine theta d theta. So it should be the case, okay, that E will end up being the integral. I'm going to pull my constants out though. So I'm going to have an integral of, let's do this. I'm going to do what I did last time and actually just deal with the cosine theta d theta business. So let's kind of just pull the math aside. So I'm going to have an integral from minus 90 to plus 90. Minus 90 with respect to the vertical of y. 90 to the left, 90 to the right. Okay? So I'm going to have that integral of cosine theta per r d theta, which is going to work out to 1 over r times that integral at its limits of cosine theta d theta. And that's just going to be 1 over r times sine theta from minus 90 to 90. And that will work out to be just going to be sine of 90 minus the sine of a negative 90 per r. And that's just 1 plus 1, because it really turns out to be sine of 90 plus sine of 90 when you apply the, you can shift that negative out of the angle in front of the sine, and a minus is a minus. So you really just get 2 over r. So that's the calculus guts of the integral. And so this part here, where's my highlighter? So this part ends up through the integral, working out to be a 2 over r. So in the end here, we would just get oops. So I'll kind of write it out sort of from the beginning with that as the backdrop. So if I were to just kind of do it all at once, it would look like this. Now you're going to squawk at this because we don't normally write K, technically speaking. Your Coulomb constant K is 1 over 4 pi epsilon naught. And so when you multiply basically this 2 over r, cuts the 4 in the denominator in half. All right? So that's just, I forgot to mention that, well, I've shown that K is that previously, but that's the way it worked out. Now, if you were actually punching in the numbers here, you know, lambda and r, and how this would work out to something, some number given actual values, which we don't have in this purely analytical problem. All right. So we have a bunch of charge distributions to go over. And if you've read in your textbook, you know, the going over that by means of calculus, deriving each one of those is a tedious, semi-irritating procedure, but nonetheless, you need to be exposed to a few of those. Okay. At the end of the day, every general shape, like a hoop or a ring or a disc or a plate or a cube or a sphere, we have static formulas that don't change. They're based on the dimensions of it, and you go and look them up, right? But every now and then you do have to revisit some of this stuff in the actual doing of science and engineering, but you'll see all that some point in the future. So that's would be the answer for this semicircular hoop. Now, if we had it at a different angle, not quite a full semicircle, then the angles would be different. You get different numbers. Okay. All right. Move on. Another charge distribution. Now, this is just like the first problem. I wished I would have put one right after the other. Didn't think of that. Because I still am adding up a charge along some distance. Okay. So I'm going to point out to you, instead of deriving this fully, it is the case for this situation, okay, that the electric field in the y direction, okay, is going to be equal to this. It's going to be K times lambda L over y times the square root of y squared plus L squared over 4. So in this one, just giving away the formula, okay? On page, let's see, page 207 of your book shows the derivation. Basically, Pythagoras meets Newton, and we have a calculus nightmare, okay? Triangles, etc., etc. All right? So it gets tedious. I don't need you to derive these formulas. if you were going to be a physics major, you'll get a chance to do that when you redo the calc-based physics sequence at a higher level, a non-introductory level. All right. So anyways, I don't get very many physics majors. I think I've had a total of 3 now in 10 years, people that said, I want to go do physics at university. Usually it's almost, this group is always engineers, with a few exceptions. All right, so that's the given formula for a situation like this. And we want to know what's the field going to be at P1, and then out here at P2 eventually. All right, so just pay attention to P1 right off the bat here. And so this formula, well, we just compute it. So continuing on here, we would have our E sub y will be k. Well, I'm going to do this. I'm going to switch from k to 1 over 4 pi epsilon naught. That's what k is. And then lambda L, the charge density, times the length would just end up being the charge Q. All right. And then I'd have this weird thing. So the y direction is an a over 2. Looking right here, that's the y distance. And so then I would have that squared. And then the L squared over 4. So it gets kind of gnarly, easy to flim when you should flam on that. And so if you go through all of the motions, k gets reduced by, or not reduced by a factor of 4, increased by a factor of 4. Is pi epsilon naught. And you have Q, the total charge, A times A squared plus L squared. One thing to note, there would be, and I'm putting this in after the fact, to be consistent with a vector representation, if that's the y direction, it's going to have that y unit vector, which we typically encode as a j hat. I for x unit vector, j for y unit vector, k for the z unit vector. Why not x, y, and z? We'd like to use x, y, and z a lot, so it might get symbol confusion. But that's the conventional way we do it. So I'm going to show you that, which means those things would convey down into the problem. So there would be a j hat here and a j hat there. Here a j hat, there a j hat, everywhere a j hat. All right. Old MacDonald had some vectors. All right. So that's the P1 part. Now P2, pretty much the same thing, except we're going to use what we learned in that previous problem. So dE, okay, for P2, all right. So this is for P1, this is for P2. The chunk of charge here, of not charge, but field, expanded form of Coulomb's constant, little k, will be lambda dx. And this is exactly what we did in the other problem, because it's the exact same setup. A thin rod, a distance away. So if I call that length x, we're in business. So this one is going to work out the same way as before. So I'm just going to write it since we've already done it. It's going to be minus lambda over the 4 pi epsilon naught, 1 over x plus a Actually, I should be more careful here. Apologize. Let me write the integral so that that's a bit more consistent. So this will move on to the electric field being, I can pull that K constant out in front and then integrate from 0 to L lambda dx over x plus a squared, right? Again, this will be in the I direction, okay, since we're going x axis on this. And just like before, the lambda will come out. There's also a negative involved in here, so I'll pull that out with it, a -1 factor for pi epsilon naught. And we'll have this 1 over x plus a evaluated from 0 to L. And surprise, surprise, we're just going to get at the end of this electric field in that x direction is going to be minus q 4 pi epsilon naught L times 1 over L plus A minus 1 over A. And again, that's going to be in the I direction. So skipped over some algebra there, just for sake of space, but it's just algebra. Oh, yeah. There we go. All right, this one's a bit easier. It's a pretty straightforward one, but I'm also banking on a standard formula. So charge is distributed along the entire x-axis. So first some decoding. Along the entire x-axis. What does that mean? That means I have an infinite line of charge. So when you get to the reading, and I have a lecture series, I think it has 3 on charge distributions, and it lays out all of this. Okay, so that's in the YouTube already. I have to upload the handouts for it for you note takers, but more on that later. So when you read the problem, I have to go, if it's along the entire x-axis, that means it's infinitely long. It means I have an infinite line of charge. And so one of the sections would be about infinite line of charge. What's the math work out in that regard? And so in the y direction, which is what we're paying attention to, okay, the formula for an infinite line of charge, 4 pi epsilon naught, or k, but we start writing it out this way because things start canceling on us. So this right here, you would find this mentioned on page 209 of your book and how it was derived. Okay, but I don't require you to derive all of them. We derive some of them and trust that you can do the calculus way for the rest of them. Well, it is the case that force, when we're talking about electric force, is defined to be Q times E. And if it's a vector, then you have those vector arrows, all right? And so that means that we would have, in this case, we would have our charge, and then the electric field is defined as 1 over 4 pi epsilon naught. And instead of charge, in the numerator, because normally it would be Q, okay, over R squared. In this case, we're talking about what's the field strength in the y direction. Okay, it would be Q over over y squared. All right, so we need to calculate it wants to know how much work does the electric field do in this business. But we also need to finish this deal here because I need to put it in terms of something that can be integrated. And what we end up getting in this game is that the force, when we resolve all of these things, we'll have a Q over 4 pi epsilon naught 2 times the charge density, the linear charge density per y, and that'll be also in the j direction. So this is what it boils down to. And now we would integrate, well, we need a work integral. And so work is going to be defined, it's always defined the same way. It's the integral along some path of the dot product of the force along whatever direction you're paying attention to. So this is going back to first semester. That is the general classical definition of work. We're used to it, work equals force times distance. And that works when you just have one small interaction, but you technically need to sum up all of the force distance pairs along some direction. All the pluses, all the minuses, et cetera, because that's what we're going to do with this integral. And so now I just write that out. I'll have some integral from a to b of q over the 4 pi epsilon naught 2 lambda per y dy. And of course, everything but the y comes out in front. Everything's a constant except y. So really, you're going to have lambda q per 2 pi epsilon naught integral a to b of 1 over y. Hopefully you remember that's a difference of natural logarithms. Hit that in Calc 1, I'm sure. And so the work, in this case, we don't have any limits, so we wouldn't know. Lambda q per 2 pi epsilon naught times natural log of b minus the natural log of a. That's our work formula. Now, the importance of this, why bother? Why can't I compute? Well, we just did a boatload of computing, okay, in the almost 3 hours of homework lecture. Real life, though, for you people as scientists and engineers, somebody's going to type the formula into lines of code. And either that will take inputs from sensor arrays and tell you something, and or it will be the input to something that follows for a control action to reverse the thrusters or turn the whatever or drop the hammer or whatever, give you a bag of chips, whatever the machine's supposed to do. Somebody's got to write the code. And just like we've done a few times in Python, that's real world. It's on a really small scale. The programs you'll deal with are going to be much larger, okay, and more complicated, connected to circuits and mechanisms, et cetera, et cetera. So all these little pieces, as you move forward in your career academically, you'll start to see, oh, and you see all this stuff kind of dogpile and go, wow, this stuff, bringing it all together becomes very powerful, but it requires you to know a lot about this kind of mathematics, a lot about this kind of physics or chemistry, a lot about this kind of computer programming, so forth, so on. You know, it all piles up over the long haul. So we do our little part here, in 10. One last problem. All right, rod's bent into this arc. So there's 2 theta. Left side is 1 theta, right side is another theta. So um, the angle is 2 theta from that center P. If the rod's charged uniformly and has a total charge of capital Q, what's the electric field at P? Okay, so what we're going to do is and we'll just have some sort of, I'm just going to let this other letter label account for the whole angle. I need something that accounts for the whole arc, because that's what we're uh, uh, trying to compute here. And so this is just for the whole arc, if you will. And so that leads me to the fact that the charge density is going to be the total charge, okay, per unit length. Linear charge density, lambda, would be total charge per unit length. And since it's an arc, a semicircle arc, that's going to be equal to r theta, but we decided to make this whole angle be the double theta. So we're going to have, we're going to use this symbol for now, just for simplicity. Do we have to do that? No. Just save our factors and not push too many letters around at once. So there is no, well, I guess it has to be the case that Q equals lambda r theta, okay? But neither here nor there, whether we do that. However you think of the linear charge density will be your, that'll be your call, all right? So now we're gonna, our variable of integration, inevitably, hopefully I don't need to tell you that it needs to be theta, right? Since we're dealing with some sort of angle. And so we're going to integrate, so the electric field would have to be equal to the integral from minus theta naught to plus theta naught, and our k constant, or 4 pi over epsilon naught. I know that 4 is going to get diminished because there's this other factor of 2 lurking around. And the electric field is going to be charge, but just like before, we are converting that to linear. So this is exactly, we just dealt with a semicircular problem before, so exact same reasoning, and instead of Q itself, I do a linear version of it. The cosine theta, hopefully you remember that comes from the fact that we're dealing with a y dimension, okay? And every one of the parts as we move across that arc is going to be adjacent to the vertical, the angle. So it's got to be cosine for the same reasons as before. And in this case, we're dealing with a minus j because it's directed down. So that's the setup. That we looked at the geometry, whether or not we needed to reduce a double angle to a single variable for the sake of ease of manipulation is your call. I decided to do it, all right? We applied the electric field equation, which is, notice that all that gobbledygook on top of r squared, that's equivalent to Q. Well, the lambda rd theta is. The cosine comes from needing the component, all right? So lambda RD theta is a geometricizing, I hope, it'd be great if that really is a word, but I have doubts, of this physical quantity called charge, so that it's integrable. Another iffy word. All right, so we set it up, and once it's set up, it's really not that uh, big a deal how this is going to work out. So we can continue the journey here. 1/4 pi epsilon naught. So I'm going to have so we'll write all this out and then discombobulate it. To finally obtain that's the final answer on that one.